Hey everyone, welcome to The Explainer. Today, we're doing something really exciting. We are going to crack open the ultimate black box of artificial intelligence. I mean, we use tools like ChatGPT, Claude, and Gemini practically every single day, but how do they actually do what they do? Today, we're going to demystify the incredible technology that powers them and really look under the hood.
Okay, let's dive into this. Is AI really thinking? Or is it just calculating? When you chat with these systems, it feels incredibly human, right? But to truly understand large language models, we have to instantly break that illusion of AI sentience.
So let's ground this in reality. A large language model, or LLM, is fundamentally just a next token prediction machine. I know, it feels like absolute magic when it writes a beautiful poem or seamlessly debugs your code, but at its very core, it is simply a giant statistical prediction engine. It looks at the text you give it, crunches the numbers, and mathematically guesses the most probable next piece of a word. That's literally it. Here is the roadmap for our factory tour today. 1. The next token predictor. 2. Inside the transformer engine. 3. The self-attention breakthrough. 4. Controlling the machine. And 5. Teaching AI human values. Let's start at the very beginning. Section 1, the next token predictor. Moving right along to Section 2, inside the transformer engine. Let's see how this builds. Think of the prompt you type into a chatbot as raw material entering a massive, highly efficient prediction factory. But the machine, well, it doesn't read words like you and I do. It only understands numbers. To bridge that gap, the model turns text into math in 4 sequential steps. First, tokenization. This breaks the text down into manageable chunks. Second, token embedding, which assigns a numerical vector, basically a long string of numbers, to each chunk to capture its semantic meaning. Third, positional encoding. This adds mathematical data about the sequence order, so the model knows exactly which word came first. And finally, the final embedding, which sums it all together. Boom, we've officially chopped up our words and transformed them into pure math. Now here's a fun fact for you. A token isn't always a whole word. For example, the word empowers is actually split into 2 separate tokens by the model. A token can be a word, a piece of a word, or even just a single character. That's exactly why standardizing the vocabulary of tokens before you even train the model is absolutely crucial for making the whole shebang work. To put the sheer scale of this into perspective, think about this massive number for a second. 39 million. In just the small version of the older GPT-2 model, there are 39 million parameters dedicated solely to the token embedding matrix. I mean, that is 39 million individual dials and knobs being adjusted during training just to assign semantic meaning to basic tokens in a high-dimensional space. It's wild. Okay, Section 3, the self-attention breakthrough. Before this 2017 breakthrough, older AI models had this nasty habit of forgetting context if a sentence or paragraph got too long, simply because they processed text sequentially. The self-attention mechanism completely solved this by processing the entire sequence in parallel, and this brilliantly illustrates the math behind it. Think of it like a web search. Inside the attention head, we have these mathematical matrices. The query, or Q matrix, is like the search text you type into a search engine. It's what a specific token is trying to find out more about. The key, or K matrix, is like the web page titles in your search results. It represents all the possible tokens that the query can actually connect with. To finish the analogy, let's look at the value, or V matrix. Once the model matches the appropriate search term, the query, with the relevant results, the key, it calculates alignment scores to see how relevant they are. These scores tell the model exactly how much focus each token should get. Finally, it pulls the actual contextual weight from the value matrix. It's kind of like clicking the link and actually reading the web page content. And the craziest part, it is playing this intense matching game for every single token simultaneously. But wait a second, if the model processes everything in the sequence at once, how does it learn to predict the next word without cheating? Well, that's where masked self-attention comes in. During training, the model applies a mask, essentially setting future token values to negative infinity during its calculations. This acts like a blinder. It strictly prevents the model from peeking into the future, forcing the machine to learn how to predict the next token based only on what naturally came before it. Moving on to Section 4, controlling the machine. So the transformer engine has successfully converted text to math, crunched the context using self-attention, and run it all through its neural networks. How does that become the final readable text you see on your screen? Well, it all comes down to output probabilities. The final linear layer of the model takes that data and assigns a raw numerical score, a logit, to every single possible token. If the model's vocabulary has over 50,000 tokens, it literally ranks all 50,000 by likelihood. It might calculate that token A has a 70% chance of being next, token B is 20%, and token C is 10%. Ultimately, the output is really just a highly educated, mathematically derived guess.
And this directly impacts your everyday user experience, because you can actually manipulate these probabilities using a setting called temperature. If you adjust the temperature below 1, it sharpens the probabilities. The model gets highly confident, predictable, and robotic, which is perfect for strict facts or coding. But if you crank the temperature above 1, it flattens the distribution. It allows lower probability tokens a chance to be chosen, creating softer, more diverse, and seemingly creative text.
Of course, too much randomness and you just get complete gibberish. That's why models use top K and top P sampling. Think of these parameters as necessary guardrails. They're filtering techniques that basically slice off those extremely low probability tokens at the very bottom of the chart. They limit the AI's choices to only a subset of the most likely tokens. This ensures that even when you crank the temperature way up for creativity, the output actually stays coherent and readable.
Which brings us to our final phase, Section 5, Teaching AI Human Values.
Up to this point, what we've built is essentially just a phenomenally complex autocomplete calculator. But a pure autocomplete calculator isn't enough to give us the helpful, safe conversational assistance we rely on today. We literally have to teach it how to behave. Now, what's really interesting here is the chronological pipeline of RLHF, reinforcement learning from human feedback. You don't just train a model once. You spend months pre-training a base model on massive text corpuses, just so it learns the mechanics of language. Then, in a totally separate phase, you train a reward model based entirely on human preferences. And finally, you use reinforcement learning algorithms, like PPO, to fine-tune that original model.
So how exactly do we get subjective human feedback into a math equation? Well, here is the RLHF process. First, the AI generates multiple responses to a single prompt. Second, actual humans sit down and rank those outputs based on what they find most helpful or harmless. Third, using an LO rating system, just like they use in competitive chess, these subjective human preferences are translated into a strict mathematical scalar reward signal. Finally, the PPO algorithm takes that numerical score and updates the model's weights to optimize its behavior.
But here's the catch. These models can be sneaky. They're actually prone to reward hacking. They'll find bizarre combinations of words that technically score high, but are total nonsense to a human reader. To fix this, engineers use a KL divergence penalty. This is a clever mathematical guardrail that constantly compares the fine-tuned model's output back to the original base model's output. If the fine-tuned model drifts too far and starts generating gibberish just to game the system for a high reward, this penalty kicks in and slaps its score right down.
Once this highly tuned prediction factory is complete, it's customized for the real world. We can fine-tune it further for specialized domains, like feeding it thousands of legal or medical documents. We can use RAG, or Retrieval Augmented Generation, to connect the model to live external databases so it can, look up the current weather. And we can even build agentic systems, giving the AI the ability to actually take real-world actions on its own.
So the crucial point here is summed up perfectly by Hugging Face. What makes a good text is inherently hard to define as it is subjective and context dependent. Despite all the brilliant math, the billions of parameters, the attention heads, and the probability sampling we've talked about today, defining what makes a good AI is always going to be a moving target, simply because human language itself is fundamentally subjective.
Which leaves us with this final lingering question. If AI behavior depends entirely on human feedback, whose human values will ultimately shape the agentic systems of our future? It's a fascinating, deeply important, and maybe slightly daunting question to chew on as these statistical prediction engines become more fully integrated into our daily lives. Thanks so much for joining me on this deep dive today, and keep questioning the technology around you.